Hi everyone, thank you for the introduction. Today I'm going to speak about Zika-Boom, a new zero-knowledge protocol for Boolean circuit. And this is a joint work with Jesper and Claudio from Aarhus University. So, zero-knowledge protocols are protocols that allow a prover to convince a verifier about the veridicity of a statement without revealing any other information. To exemplify this concept, we are going to consider this situation in which we have two players, Alice and Bob, and they both know a public circuit C and a value Y, and Alice also knows a private input X such that C of X is equal to Y. And a zero-knowledge protocol is simple, an interactive protocol between these two players that allows Alice to prove to Bob that she knows X without revealing information on X. So, since their introduction late in the 80s of zero-knowledge protocol, they have been used in cryptography to design many complicated protocols. For example, we have signature schemes that are based on zero-knowledge protocols, user identification protocols, electronic voting system, and so on. So if we would like to see all these applications, all these interesting and nice applications to become alive in our real world, the first step that we need to do is designing practically efficient zero-knowledge protocol that can be used to prove a general statement. And with practically efficient, I mean protocols that they don't only have good asymptotics, but protocols for which this asymptotics comes with small constants, small and non-constant. And if we look at protocols, zero-knowledge protocols with these two features, the state of art, we find these two approaches. The best approaches are these two. So the first one is represented by this family of protocols that are referred to with the name of snarks, that stands for such non-interactive arguments. And the good properties of these protocols is that they usually have very small proof. Many of them, they have a constant size proof. And they are very short, very small verification time. So the proof that they can be verified in short time. On the downside, we have they need a setup phase in which large keys then needed to be generated. Can you hear me? Yes. Okay. And they are slow in improving. So meaning that the times then Alice has to wait to generate the proof is bigger. And this is because basically they all use many of them they use a heavy cryptographic tool that is pairing. Many of these protocols have been implemented, and in particular in this talk, as term of comparison, I'm going to consider Pinocchio. That is one of the implementation of snarks. The other approach is represented by zero knowledge from garbage circuits, and as it says the name, it's based on Yao protocol for garbage circuits. And the nice thing of this approach is that now the proving time is decreased with respect to the snarks protocol. But this protocol is interactive and it cannot be made non-interactive. So interaction is required here. And beside these two options, you finally now have a third one that is represented by Zika-Boom. Zika-Boom, it's a 3-round protocol, but it can be made non-interactive. It's very fast in both improving and verifying. So Alice and Bob, they have to work more or less the same now. And we pay this improvement in the running time with the fact that now the size of the proof is not constant anymore, but it's going to be linear with the size of the circuit that is the circuit that represents the statement that Alice wants to prove. So before explaining what is Zika-Boom, let me give you some details to explain what I mean when I say short, when I say fast, when I say slow, okay? So these are the results from our experiment to prove the knowledge of a pre-image of an hash value that is computed using the hash function SHA-1. So if you look at the second column, you can see that the proving time, so the time that you have to wait to generate the proof, the Zika-Boom protocol is much better than Pinocchio. 1,000 times better. So this is only 13 milliseconds, and here it's 13,000 something, 12,000 something. The verifying time is more or less the same, few milliseconds for both algorithms. But then if you look at the size of the proof, so how many bits Alice needs to communicate to Bob, Pinocchio has this nice short proof, around 300 bytes, while we have a bigger 450 more or less kilobytes. Okay, so there is a difference also in this column. And in the middle of these two situations, let's say, we estimate that we estimate the complexity of zero knowledge from garbage circuit. So in the rest of the talk now I'm going to describe Zika-Boom, and at the end I'm also going to give you more implementation results. So let me start this first part with a definition. So I'm going to define what a sigma protocol is. So we have this public circuit seed and the public value y, as before, two parties, Alice and Bob, and Alice knows x, such that C of x is y. A sigma protocol is an interactive protocol with 3 rounds of communication, and they need to be of this exact form. So the first round is a message from Alice to Bob. Then the second round is a random message sampled by Bob and sent by him to Alice. And then at the end we have the last message that is the answer that Alice is going to send to Bob to answer to the challenge E. And at the end Bob is going to answer yes or no. And we want Bob to answer yes when he is convinced by the fact that Alice knows X. So we want the protocol to be complete, clearly. And then we want 2 security requirements. First of all, we want security against a cheating Alice. And this is formalized as saying that if Alice knows the answer to many different challenges, then from the answers we can compute X. So we are sure that Alice knows X. A way to measure how good the protocol, a sigma protocol, is against a cheating Alice is considering the soundness error. The soundness error is a bound for the probability of Bob saying yes when Alice is trying to cheat. And we want this, of course, to be small. Okay? Then we have the security requirement against a cheating Bob, okay, for a cheating Bob. And this is what we call the zero knowledge property. And basically we want that from the 3 messages that are exchanged during the protocol, Bob cannot infer any information about the original input X. Finally, observe that the fact that we have these 3 rounds where the second one is just a random message made possible to use standard techniques like the Fiat-Shamir heuristic to squeeze these 3 messages to be only one and made the protocol be non-interactive. Okay? So I can consider these kind of protocols non-interactive, basically. So now that we have this definition, this very nice definition, and we have very clear in mind what we want to achieve, how can we achieve it? So there is a very beautiful construction of sigma protocols in this paper of Ishai and others from 2007. It's called the IKOS construction from the names of the authors. Or also is known in cryptography is known also with the name of MPC-in-the-head because the entire construction is based on a simulated MPC protocol. In this paper you can find a sigma protocol which soundness error is 2/3, but the main result of the paper is a zero knowledge protocol with good asymptotic complexity. So Zika-Boom, you can see it as a new interpretation of this setting that has the main goal of designing a protocol that is practical or close to practicals. And the main ingredient to achieve this was basically considering, instead of MPC protocol, considering this new primitive, new tool that we call circuit decomposition. So a circuit decomposition is just a way of computing a circuit on a value by splitting this computation in 3 different branches of computation in such a way that when you look at 2 only of the branches, then you don't know which was the input value. Let me explain this better. So we fix a parameter n, okay? And then we consider a family of a function, the function that you can see in the box in the slide, okay? And we are going to use this function to compute C of x in this way. First of all, we use the share function, okay? And we split the input x in 3 values, w01, 02, and 03. Then in our box, we have these n sets of 3 functions each. And I'm going to use this n set in n steps in my computation. And each step, in the first step, I use the function from the first set, and I'm using them in the following way. So I take the first function, I input the value from branch 1 and branch 2, and I compute the next value in the branch 1. Then I take the second function in the set, and I input the value in the branch 2 and branch 3. So always consider the branch on the right side also. And I compute the second value in the second branch. The same for the third branch, okay? And so on. I do this n time. And then I recollect all these values with the reconstruction functions, and I compute this output value, the output value of the reconstruction y, and I say that the composition is correct if y is indeed C of x. And I say that is true private if, when I look at the values, the intermediate values, the w values, in 2 branches, 2 consecutive branches, then I cannot know anything about the original x, okay? So, given this, I'm now going to show you how to construct a zero-knowledge protocol, given a function circuit decomposition. So the first step is ask to Alice to compute the entire decompositions, as we did in the previous slide, okay? Then she's going to commit to the w values, so all the intermediate values that have been computed. If you don't know what a commitment is, this just means that Alice is going to put all these values in black boxes and she sends these boxes to Bob. Bob cannot see inside the boxes because the boxes are black and they are closed with keys, but Alice has not anymore the values now, so she cannot change the values inside the box. Now Bob has to choose a random index between 1, 2, and 3. And Alice, she is going to answer to the challenge of Bob, opening the commitments, the boxes of branch E and E plus 1, okay? In this way, now Bob knows these 2n values, and he can run a part of the functions in the decomposition, right? And can check that these values, they were computed by Alice in the right way. For example, you can check the W11 is F11 of W01 and 02, okay? And if everything is okay, it's going to output yes, otherwise no, clearly. So this is a Sigma protocol. I mean, it has the right decomposition, right communication partner, clearly. I mean, the zero-knowledge protocol, it's very easy to see because if the circuit decomposition has true privacy, then Bob doesn't know anything about X from the values that he can see. And finally, observe that he has soundness errors 2/3 because basically if Alice knows how to answer to all the 3 possible challenges, this means that she knows how to compute the complete circuit decomposition. So in particular, she can compute the value of step 0, and she can compute using the reconstruction function here, she can compute x. She knows x. So this is Zika-Boom, and this is just what I show you now is just basically general reduction that, given a circuit decomposition, gives you out a zero-knowledge protocol. If you want to implement a zero-knowledge protocol, then you have to decide which circuit decomposition to use, right? So in our paper, for the circuit that we were looking at, Boolean circuit, the best decomposition was this one, the linear decomposition. In the linear decomposition, n is equal to the number of the gates in the circuit that represent the statement, okay? And this is what gives you linear size proof. Then the share and the reconstruction function are just the sharing and reconstruction algorithm of the additive secret chaining scheme. So you split a value in the sum of 3 random values. And then to define the function for the family F, you define one set of function for each gate in the circuit, and the definition depends on which gate you are considering. So if you have XOR gate, the definition is very simple. So you just sum locally in a branch the 2 input values. Instead, when you have an AND gate, it's a bit more complicated because you have to consider now the pairwise products coming from that branch and the branch on the right side. And you have also to mask this computation with an ad hoc random value. All the details, of course, they can be found in the paper. So using this decomposition, we run some experiments. And you can see the result in this slide, in this table. This is our, as you can see, this is our for proving the pre-image, the knowledge of the pre-image for SHA-1 and for SHA-256. So for SHA-1, the proof size is around 450 kilobytes, and it's more or less the double size for SHA-256. And so these numbers are all for soundness errors to the -80. That's what is used in practical application. And I show you, the Zika-Boo protocol has soundness 2/3. So if you want soundness 2 to the -80, you have to repeat the protocol. And actually, the fact that the proofs are done for this soundness error are done in repetitions makes it very useful to use parallelization. If you try to parallelize the implementation, then you can decrease a lot the running time both for the verifier and the prover, for Alice and Bob. The implementation is public. You can find the code that we used to run the experiment on GitHub. That's the address. Let me now recap a bit and then conclude with some open questions. So Zika-Boom is close to practical zero-knowledge protocol that is basically non-interactive. It is already implemented for SHA-1 and SHA-256. And has proving time much smaller than the current technology for SNARK. And it has a better name than SNARK. Let me conclude with this remark. So in this paper, we focused our attention on the Boolean circuit because we consider SHA-1 and SHA-256 for the experiment, so it makes sense to consider a Boolean circuit. But Zika-Boom, with the linear decomposition, it can work for any circuit, Boolean or arithmetic. So this allows us to think that there are at least two new direction in this research. Because first of all, it will be very interesting to implement general purpose zero knowledge, Zika-Boom, meaning just having a code where you input the circuit C, and then the proof is generated using the Zika-Boom framework. The second new research direction is more related with the design of Zika-Boom. And since this Zika-Boom can work for any circuit decomposition, why not consider it, take your favorite circuit, for example, the circuit compute AES encryption, and think about designing an ad hoc circuit decomposition, ad hoc for that circuit that allow you to decrease the size of the proof generated by Zika-Boom. And I said everything, so thank you for your attention.
Great. Questions, please.
Thank you. In one of the previous slides, you've shown the number of AND gates for each of the circuits. Yeah. Are we correct to assume that the runtime is dominated by the number of AND gates in the circuit for the function?
Exactly. Yes. The XOR gate is for free, basically, in the linear decomposition, because I skipped some detail, but you can basically embed the XOR gate in the AND gates. So it's linear in the number of AND gates, the size.
Right. So this is just a standard implementation of Ishai. It's not particularly optimized for the number of AND gates, correct?
Sorry, say it again?
So these are just for standard textbook implementations of Ishai as a Boolean circuit?
No. Both the circuit that we used, we tried to minimize the number of AND gates.
Okay, thank you.
Yeah.
So I saw on your second to last slide you say nearly practical.
Yes.
All right. So what is it in your mind that isn't fully practical?
Depends on the application. I think the size of the proof can be still too big. The running time, no. That side of the running time, I think we are practical. We can say that practical, but the size of the proof is a bit too much.
500K?
Depends on application.
Yeah. Right. Anybody else? All right, let's thank our speaker.